Good morning, good afternoon, good evening, wherever you are. Welcome to JWebbinar 42 on JWST and the NASA AmesPAH Infrared Spectroscopic Database, or PAHdb for short. My name is Christian Boersma and I'm the PAHdb lead. It hasn't passed our notice that this is the 42nd JWebbinar, so we thought it appropriate to rebrand it as the Ultimate Astronomer's Guide to PAHdb. We will have a number of exercises, and for the exercises, we will go through the solutions together to not spend too much time on them. It should be noted that we do expect participants to know to at least some extent what PAHs are and are familiar with Python. Before we get started though, some acknowledgements and thanks are in order. First of all, our thank goes to the STSCI for hosting this JWebbinar. Furthermore, they just brought a laboratory astrophysics resource page online with information on PAHdb, as well as there are now direct links to the PAHdb tools on their tools for the community page. Links are shown here. Second, we would like to acknowledge the Laboratory Astrophysics Directed Work Package at NASA Ames for funding. This is a team of researchers that provide a synergy between Ames lab, theory, and astronomical research. The agenda for today is as follows. This JWebbinar has been broken up in 3 parts. In part 1, a general introduction is provided, followed by a live demonstration of the PAHdb website and 2 exercises. In part 2, Alexandros Markoudakis will introduce and demonstrate the use of the AmesPAHdbPythonSuite, followed with 3 exercises. This is then followed by a quick update on our PyPAHdb tool. We wrap things up in part 3 with an outlook, part 1. PAHs are everywhere and anytime. Shown here is the gorgeous NearCam image of the Orion bar by the PDOS4All team. It highlights many interesting embedded objects and structures. Much of the mission can be attributed to that originating from PAHs, here encoded as part of the green color band. Another exciting one is the mirror image of the binary Wolf Rayet star system WR140 from ERS program 1349. The image displays beautiful rings that are shining in PAH emission here, encoded as red. This is a mesmerizing mirror image of the Phantom Galaxy as observed by the FANGS team. Emission from PAHs is observed throughout this galaxy. However, JWST is not only about beautiful images. Depicted here is a mirror spectrum of the galaxy NGC 7469 as observed by the GOLS JWST team. The main PAH bands have been indicated, and the comparison is made to its counterpart Spitzer spectrum. It demonstrates the incredible increase in spectral fidelity JWST brings to the table. As for any time, here's the 3.3 micron PAH feature at a redshift of 4.22 as detected by the templates team. This mirror spectrum has been corrected for redshift and is compared to the 3.3 micron PAH feature in the near-spec spectrum of a nearby galaxy. Lastly, turning back to our own galaxy, this is the 1 to 5 micron near-spec spectrum of M17 from Cycle 1 program 1591. It depicts a strong 3.3 micron PAH feature, but also many other features related to PAHs. Diving deeper into the spectroscopy, here is the 3 to 20 micron JWST spectrum of the atomic PDR in the Orion bar, crudely removing the atomic and molecular emission lines, as well as an automated spline continuum isolated the PAH emission bands, here indicated in the inset with the dashed blue lines. Zooming in, many of the bands can be attributed to fundamental vibrations in PAH molecules. Here these are depicted for the 3.3, 6.2, 8.6, and the 10 to 15 micron bands. The main goal is to explain the richness of the astronomical infrared PAH spectrum, and through this gain an understanding of the astrophysical and astrochemical environment. The carrier of these bands are a mixture of PAH and PAH-related species. Focus on the mixture. So the question is then how to obtain the needed variety. One way forward is to extrapolate from the limited laboratory measurements available and use computed PAH spectra to create a library of PAH spectra. Thus, thereby, Combining a spectral library plus astronomical modeling and simulations would then allow analyzing and interpreting the observed astronomical path spectrum. There are 3 databases that we are aware of: the Italian-French one at NIST, and of course the NASA AmesPAH Infrared Spectroscopic Database, or PAHdb for short. Here we will be focusing on PAHdb. PAHdb has 3 pillars: PAH spectral libraries, software tools, and a website. To ensure the community can readily make use of PAHdb, each of these pillars has extensive documentation. Let us now briefly touch on each of these. As spectral libraries are concerned, PAHdb offers 6. There is a library of harmonic computed spectra, which currently holds almost 11,000 spectra, that of laboratory measured spectra, which holds 84 spectra, that of laboratory measured PAH cluster spectra, which currently holds 9 spectra, that of harmonic computed PAH clustered spectra, which currently holds 103 spectra, that of anharmonic computed PAH spectra, which currently holds 11 spectra, and that of laboratory measured gas phase PAH spectra, which currently holds a single spectrum. It should be noted that not all these libraries are currently publicly available yet. The bottom left figure shows the accuracy of the harmonic computed bands positions when compared to the laboratory measurements. There is less than 0.5% the statistical differences. The bottom right histogram shows the charge breakdown in terms of path size of the library of harmonic computed path spectra. The cross-hashed areas indicate the spectra that have been added to the forthcoming version 4 of the library. Moving on to the PAHdb website. The PAHdb website is the main portal where one can peruse the contents of PAHdb's libraries, download the data, and use some straightforward tools. Next are the offline software tools. We offer a suite that can be used with IDL, one that can be used with Python, and a specialized PyPAHdb Python tool that has been developed as part of the PDFs for All ERS program. Alexandros will go into some detail on the Python suite later. Of course, then there is the documentation that is accessible through the documentation portal. There's documentation on every aspect concerning PAHdb. Beyond that, there is a cookbook with some basic and more advanced data analysis recipes. So what are then some different approaches to make use of the data, models, and software tools offered through PAHdb to analyze and interpret astronomical PAH observations? The first is a straightforward approach where one takes predefined mixtures of PAHs, computes their spectra, and directly compares them to astronomical observation. This is done in this figure. Another approach is to derive specific relationships that can then be included in more general models. For example, here's the relationship between the number of hydrogens and the integrated cross-section of several PAH bands given. Yet another approach is to create diagnostic diagrams like the one shown here. One can then take PAH band strength ratios determined from the observations, place them on the diagnostic diagrams, and read off, in this case, PAH charge and size information. Finally, there is the powerful approach of fitting the PAH component directly. This is demonstrated in this movie. Alexandros will go through a detailed demonstration with you doing this later. This takes us to a demo of the PAHdb website. This takes us to the landing page, which follows a vertical layout with at the top the PAHdb logo, below a menu bar with 6 links, below that a search area, below that radio buttons for selecting libraries, and below that links to relevant and timely information, like the announcement of this JWebbinar. Let's start by looking at picking libraries and versions. We can click the versions link to arrive at these tables, and they show the different libraries with their version. A particular library and version can be selected by clicking one of the radio buttons, like so. Early versions are kept around to ensure results from using those outdated versions can be reduced. Let us keep to the latest version of the library of harmonic computed PAH spectra. We can click now up here, the menu bar has moved up here. We can now click the browse menu item to start exploring the content of this library. Shown are the chemical structure and the chemical formula of the different PAHs. Hovering over a structure, so, will show a slight blow up. As you see, it indicates a UID. Each PAH in PAHdb is given a dedicated UID that stays consistent across versions and between libraries. One can browse the different pages, page by page, like so, or jumping pages. Clicking a chemical formula, for instance this one, loads up that PAH's dedicated page. It shows a 3D interactive chemical structure and an interactive spectrum. Beyond that, a number of details are presented. Transitions are tabulated under the Transitions tab. Give it some time to load. Clicking a row will visualize the corresponding fundamental vibration. Not all PAHs have cluster computations, but our current PAH does. Under the Cluster tab, an overview is given of the available configurations with vertically organized the number of monomers and horizontally their different configuration. Clicking one of the links takes you to that cluster's dedicated page. Like we saw before, a 3D interactive rendering of a molecular structure is shown as well as an interactive spectrum. Transitions and corresponding fundamental vibrations are visualized as before. Since this is a large file, we ask if you really want to load it. It takes a few seconds, and then indeed clicking them. The Download tab can be used to download the data associated with this specific PAH cluster. Going back to the monomer by clicking up here. Here we also find the Download tab. One can choose to download here the data on the monomer itself or all the cluster data we saw before. You might have noticed the box saying this species has a counterpart in the experimental library. Clicking the link takes us to the experimental counterpart. Similarly as we saw before, we get detailed information about this PAH, though the Transition tab now tabulates the laboratory measured transitions. Clicking a row highlights the corresponding band in the interactive laboratory spectrum shown here on the right. For this particular PAH coronine, there are also cluster measurements available. These are directly shown inside this tab. The Download tab is the same as before. As you might imagine, going through some 85 pages of PAHs to find the ones you are after can be somewhat cumbersome. To that end, we can make use of the website's search case capabilities. Going directly to the search bar might be tempting, but looking first at the advanced page will provide an impression of what can be searched for. Here you see one can search by name, UID, number of atoms, or any other parameter. PAHs that reach a certain intensity in a given intensity range, or a boundary edge code that uniquely describes a PAH geometry. Let us search for a very popular PAH coronine. Hit search. Indeed, this way the 4 coronine molecules, each in a different charge state, are found. Note how the search bar now contains the syntax that's being used, so simply the name. The check boxes here can be used to select them. Let's do that. 1, 2, 3, 4. You might have noted that the selection menu item is now decorated with a number of PAHs selected. Clicking it allows you to manipulate your selection. With our selection made, we can click the Download menu item and choose to download the data associated with our selection. Besides that, we can also download entire databases at different versions. Besides the data, the right side of the page provides information on the PAHdb software tools. However, some rudimentary tools are also offered directly on the website by clicking Tools. At the top of the page, modeling parameters can be set, such as the line profile to use, path emission model, etc. etc. Tools will use the paths that have been selected. This is indicated here. For example, we can click here the Co-op button. This executes the tool and presents the results on the results page. Note that a PostScript version of the figure can be downloaded as well as the data beyond the figure. Before going to the first exercise, I would like to point out the help, which provides more background information, a website tour, as well as several instructional PAH-related videos. For instance, I think we're also linking to the JWebbinar 23 here. For the first exercise, we want to compare the 2.5 to 15 micron neutral and singly ionized cation spectrum of the PAH choranine, which we just looked at. You will need to find and select the right paths and use an appropriate tool. Once you've done that, what is most striking and how can this be used astronomically? Let's take a couple of minutes for this, after which we'll look at the solution together. So please visit the website and see if you can do this exercise. Okay, let's take a look at the solution together. There we go. On screen is the figure resulting from using the stack tool. Most striking here is the change in relative intensity between about 6 to 10 micron. One and often used astronomical application is to take a band between 6 to 10 micron and ratio it to, for example, 11.2, and by that way track path charge. Okay, moving to the second exercise. Here we want to compare the 2.5 to 15 micron spectra of 5 neutral paths in the choranine series. You will need to select the paths with the UID 18, 37, 108, 612, and 615. Subsequently, apply the full cascade emission model and make use of the stack tool again. Again, what is most striking and how can this be used astronomically? Able to get to the website. So there are several ways of doing this. So we need to first find our paths with this UID. So we can go to the advanced search. We have the UID search here. So we can just look for one. Search, and there it is. We already have it selected, so because I had the previous demo. So let's select none. Let's go back to our advanced search. So we can select them, search for them one by one, like so. Or more advanced, we can add an OR class, and we can put here 37. And let me search. Oh, don't know why it still shows choranine. But this way you do see the syntax that's being used. So it says UID equals 18 or UID is 37. So we can expand on this by, for example, doing or UID equals 108 or UID equals 612 or UID, let's see, I need to move my window, 615. Then we hit search, and then they are all 5. So up here, selection, there is a, you can select the search results all in one go. So now we have selected them all. So then we go to the tools and and set our transitions to be between 2.5 and 15 micron. We can give it any line profile we want. We keep the same full width half max. We would like to apply an emission model, so we can do the most advanced one, a full cascade, and then we say 8. And then again, we use the stack tool. So here we go to the stack tool and click that. Give it a minute. Some of these paths are quite big and it takes a little while to compute the cascade model. Here we see our 5 spectra, and I think 2 things can be noted. One, well, 3 things in a way. Well, the first one is that they get progressively larger, the paths. Second is that the temperature they reach, which is indicated here under their formula, decreases as the path gets larger. But what I specifically would like to draw your attention to is how the strength of the 3.3 micron band here almost vanishes relative to, for example, the 11.2 micron feature. So here it's the same figure, and highlighted is the change in the relative intensity of the 3.3 micron feature, and the astronomical application is that one and often used astronomical application is to ratio the 3.3 micron band to the 11.2 micron band to track path size.